Okay, what I'd like to do now is really talk to you about another system. This is going to be an alarm system, actually a realistic alarm system. And here is a specification of what we're going to design. Now what we have here are external inputs to the system. It's a state machine. So we're going to have an arm-disarm switch, which is a debounced momentary switch, which is going to be fed into an SR latch. This switch is first used to arm the system, and then the same switch will be used to actually disarm the system. And we're going to call basically the output of that switch, we're going to call it AD. So that's really the output of the switch SR latch combination. So it's really coming out of the SR latch. There's going to be an intrusion input. We'll talk about how we might generate such an input in a moment. As a carry out, which is coming from a counter, and that's going to be used for a timeout feature while we are in a siren state where the alarm is going off. Outputs that this system needs to generate, there's going to be a green LED. Now that's going to indicate that the system is really ready to be armed. There's a red LED, which will indicate the system is in an armed condition. Then there's going to be a clear. This signal is used to clear the counter. It's a low acting signal. There's a reset signal, really for the SR latch, and then there's an SR signal, which is really going to activate the siren. And we're assuming basically all the I/O are high acting, unless otherwise specified, and this is really the only one, which is the counter clear over here. All right, let's talk a little bit about this idle condition. Okay, so there is an idle state. Now this actually may be more than one state. But if the intrusion input is a 1, what we're saying here is that the system cannot be armed and the ready light is going to be off. If the intrusion input is a 0, then the system can be armed and the ready light is on. Let's talk about the armed condition. A red LED is used to indicate the system is in the armed condition. The system can be disarmed by the AD switch. If the intrusion input becomes a 1, then the system will go into the alarm condition. Otherwise, the system will stay in the armed state unless disarmed. There may be more than one state for this armed condition. All right, alarm condition. In the alarm condition, the siren is to stay on for 16 clocks, and a 4-bit counter is going to be used for the siren timeout. The system cannot be disarmed while in the siren state or the alarm state. So our task is really to design this system. All right, let's look at this idle condition, all right? Now, let's just draw a state box to actually start with, all right? And while I'm in this particular state box, let me look at the intrusion input. So that's the INT input, okay? There it is. Now, if this intrusion input is equal to a 1, then I'm pretty much going to stay in this state, okay? This is like an idle state. All right, if the intrusion is a 0, which means basically if it's a perimeter protection on our alarm system, it means all doors, windows effectively shut, we will move into the next state. And in this next state, we're going to turn on the green LED, okay? Now, let's once again look at that intrusion input. So here it is. Now, if this intrusion goes back to a 1, which might mean that we've opened a window or we've opened a door, then we're going to simply move back up to this condition here. And we'll loop around in this condition until the intrusion input goes away, and that is where all doors and windows, let's say, are closed, and then we'll move into this state. Now, if the intrusion is a 0, then we can look at the input coming from the arm disarm switch. So here it is. Now, if this is 0, that means we're not arming the system, then we're simply going to stay in this particular state. On the other hand, if we are arming the system, and we can only do it really from this particular state here, when the green LED is on, then we will move over, and we're going to move over into effectively an armed condition. So we'll move over here into an armed condition, and we're going to turn on the red LED in that particular state. So we've got to think about really how we might disarm the system while we're really in this state. Now, since we're using AD coming from our SR latch to arm and disarm the system, then we really should in this state generate a reset signal, and we'll call that RS. Then we'll move into another state. In this other state, we're going to turn on the red LED, so it's still the armed state. And then at this point, we can actually look at the AD arm-disarm switch. And if this is, let's say, a 0, we can then look at the intrusion input again. And if the intrusion input, let's say, is a 0, then we're going to simply stay in this particular state unless we actually disarm, okay? So if we disarm the system, that's when we make AD a 1, then that will allow us basically to perhaps come back all the way over to here, like so. Now, if we do this, don't forget, we've actually set the SR latch, that's become a 1, and we've moved over to this state. So really in this state over here, we should generate that reset signal. All right, now if intrusion, of course, is equal to a 1, then what's going to happen? We're really going to move into basically that siren state, okay? So let me just show this by coming over here a little bit. So here we go. We're actually moving into the siren state itself, okay? So here it is, the siren state. All right, so we're going to basically turn on the siren. Now, we're using a counter, are we not, for a timeout feature here? Yes, we are. And so therefore, really, we need to be sure that effectively the counter has been cleared. So how would you do that? Well, you could clear the counter here, but you can't look at the carry out from the counter while in the state. We would actually need to generate another state. So let me just show you that. We could generate, if you like, the LCLR while we're in that state. Then we would have to move into another siren state. So the siren is now on here. Then we can, of course, look at the carry out. And if the carry out was, let's say, a 0, we will stay in that particular state. If the carry out is a 1, then we can come out. And then, of course, we can come right back up to the beginning again. Now, the only thing to note here is if we actually do this, okay, then we've got basically the siren on for how long? Well, we've actually got the siren on really for what? 16 clocks here, and then an additional clock over here. Now, the spec said you only want to have this siren on for what? 16 clock periods. Well, a quick fix of that would be what? Well, just don't generate the SR signal while you're in that particular state. Just don't do that, okay? So that's one approach here. Or alternatively, you could say, I could probably get rid of this state entirely, and I really would like you to maybe think about this. Perhaps we could pause at this point. You have a little think about this, and really, you could actually generate the clear over here, could you not? Okay? So that's something for you to think about, all right? So we could actually save ourselves perhaps a state if we actually do that. Now look, before I actually pause this, I want to talk to you a little bit about how we generate that intrusion input. Intrusion input. Let's think a little bit here about a switch. Now, I'm going to call this it's a little magnetic, and it's a read switch, okay? Now, how does this guy actually work? Well, basically, it's a switch that is held in a closed condition by a magnet. All right, so what you'll see is, and I'll attempt to do a little drawing here. You have a little magnet, okay? And this is my little magnet. okay? And this this is in close proximity, let's say, to a little switch. So here is the switch part. So this is really the magnet. And then this part over here is basically the switch itself, okay? So here it is. You can buy these at various electronics outlets. And it's got two wires coming out of it, okay? So that's the actual switch itself, and that's a magnet. Now, when the switch is in close proximity to that magnet, this switch is basically in a closed condition. If you move the magnet away from the switch actually opens up, okay? So you might, look, we could attempt to do a little drawing here of that switch. We could say that, okay, inside there's kind of like a little reed over here. There's the wire coming out, and we could have the other side perhaps looking like this, the wire's coming out like this, and it is in an open condition if there is no magnet close to it. If I now put a magnet close to this, so once again there's my magnet, then this magnet will cause this guy, this little reed, to actually move in this direction, and it makes contact, and it's therefore in a closed condition. All right, so these are very common type switches. As I say, magnet closed, or rather magnet is close to it, the switch is in a closed condition. Remove the magnet, the switch is in an open condition. So you can imagine a situation, couldn't you, that perhaps you have a door, or a window for that matter, but let's look at a door. So here is the frame of the door, okay? And we can visualize perhaps the door can open like this. So on the frame of the door, what we would have is the actual little switch itself. So that would be my switch. But actually on the door part, you could imagine that really you actually have the magnet. Okay, so there is the magnet. So when the door is in this open condition, what is really happening to that switch? Well, that switch would now be open. Okay, so it's in an open condition. If I close the door, the switch is then in a closed condition. Now, I guess the question is, how can we utilize that feature to provide, let's say, an intrusion input? Okay, now imagine that I've got, let's say, a voltage source sitting over here. I'm going to say that that's 5 volts. Okay, I'm going to put let's say, a resistor in over here, maybe a 470 ohm or 1K type resistor. And let's model this as a series of switches like so. So this could be a door, and that's in series perhaps with a window switch. That's in series maybe with another window switch, and perhaps in series yet again with another window switch. And the other side we're simply going to tie to ground. The other side of the power supply, of course, to ground. So we have a circuit now, okay? We're going to take an output over here, and that's going to be our intrusion that's going to be an input to really the state machine itself. Now let's consider this. Now remember that each one of these switches, that could be a door, has a little magnet there keeping it in a closed condition. This could be a window, magnet keeping that guy in a closed condition. Another magnet here keeping this window, let's say, in a closed condition, and maybe another magnet sitting over here keeping that guy in a closed condition. Now, as soon as you open, let's say, a door, what happens? You actually not remove the magnet, but the magnet then is no longer close to the switch, and therefore the switch opens up. We saw that in the case of the door. Same story with the window. If we open the window, okay, we remove or move the magnet, I should say, away from the little switch. And so therefore the switch moves into an open condition. Since all of these are in series, any one of these switches opening up will cause this intrusion to actually go up to 5 volts or become a logic level 1. And that's basically how we're dealing with producing an intrusion signal that's used with our state machine. All right, let's take a little break. Once again, I want you to have a think about redrawing that state diagram and reducing one of the states there. All right, I'll see you next time.